The way that we can figure this out is using something called bond order. And bond order is equal to 1/2 times the number of bonding electrons minus the number of antibonding electrons. And the bond order you get out will either be, for example, 0, which would mean that you have no bond, or you could have 1, a single bond, 1.5, a 1.5 bond, 2, a double bond, and so on. So let's figure out the bond order for our two molecules here that we figured out the electron configuration for. So I guess we'll start with helium-2. So the bond order is going to be equal to 1/2, and then it will be 2 minus 2. So our bond order for He2 is going to be equal to 0. So it has a 0 bond. There's no bond in He2. Let's look for hydrogen. For hydrogen, our bond order is going to equal 1/2, 2 minus 0. So we would predict a bond order of 1. What kind of a bond is a bond order of 1? Yeah, we'd expect to see a single bond in hydrogen. So what it actually turns out, the reality is that He2 does exist, but it exists as the weakest chemical bond known, and it wasn't in fact even found to exist until 1993. So I can assure you this is not a bond that you see very often in nature, and it is a very, very weak bond. It only has a dissociation energy of 0.1 kilojoules per mole. So that should make sense because we saw no energy difference between the actual atoms and the molecules. Molecular orbital theory, even at this very basic level, allowed us to predict that no, we're not going to see a true bond here, a strong bond. In contrast, the dissociation energy of a bond for hydrogen, and molecular hydrogen is everywhere around us, we see 432 kilojoules per mole. All right, so we can now see a little bit of what the power of molecular orbital theory is in predicting what kind of bonds we're going to see in molecules, or whether or not we'll see this bonding occur at all. So let's look at another example. Let's take lithium-2 and see what we can figure out here. In lithium-2, we have 2 atoms of lithium. Each have 3 electrons in them. So now we have to include both the 1s orbitals and also the 2s orbitals. So anytime in a molecular orbital diagram you draw in orbitals, you need to draw the corresponding molecular orbitals. So this means we need to have sigma 1s, sigma 1s star, and now sigma 2s and sigma 2s star. Something I'll also point out is you see these dashed lines that tell you where the individual molecular orbitals are arising from. As you get to higher and higher atomic numbers of molecules that you're making, it makes a lot more sense to look at a diagram when you draw these dotted lines in, because they can start to get a little bit confusing. So when you go ahead and draw these on your problem sets or on your exams, it's a good idea to put these dashed lines in, both for you and for people reading it, to see exactly where your molecular orbitals are coming from.